Hi, this is a continuation of the 2B equilibrium constants notes where I will show you some sample problems. In sample problem number 3, we're given equilibrium concentrations of reactants and products for the following balanced chemical equation from two experiments, experiment 1 and experiment 2, and we are supposed to calculate the KEQ for both of them. For experiment number 1, the KEQ will equal to the concentration of SO3, which is 3.50 molar, and the superscript will be a 2, so squared, over the concentration of the SO2, which is 1.50 molar, and its superscript is a 2, times the concentration of the oxygen, which is 1.25 molar, and I didn't really need that 1, but its superscript is a 1, so I won't write that. And when you solve this, you'll get an answer of 4.36. Now I'll do the same for experiment number 2 and show you the result. Notice that the two KEQ values don't have units and that they're very similar to each other. Any differences we see would probably be due to experimental error. You should do these calculations, and if you're having trouble with the mathematics of it, please see Ms. G. In sample problem number 4, we're asked to solve for the concentration at equilibrium of one of the products. We're given the KEQ value of 8.96 times 10 to the negative 2. And we'll set that equal to the concentration of one of the products, PCl3, which is 0.300 molar. The coefficient is 1, times the concentration of the chlorine, which is Cl2, and that's what we're solving for, over the concentration of the PCl5, which is a reactant, which is 6.70 times 10 to the negative 3rd molar. When we solve for this, we'll take the 8.96 here times 10 to the negative 2 times 6.70 times 10 to the negative 3. We'll divide by 0.300, and that will give us the concentration of the chlorine. And when we do that, we should get an answer of 0.00200. I want 3 significant digits there, and it's a concentration, so it's a molarity, and that's it. Equilibrium constant expressions are dependent upon coefficients in a chemical reaction. So they're related to equation stoichiometry. The way you write a chemical equation will affect the value of KEQ. Let me give you an example. Here's a forward reaction, N2O4 producing 2NO2. Here's the equilibrium constant expression, products over reactants, and we're given a value for the KEQ at 100 degrees Celsius. If we were to write this reaction in reverse, we will get the inverse of this KEQ as an answer to the KEQ value of the reverse reaction. If we were to write the KEQ expression for the reverse reaction, here I've already written the reaction in reverse, it's going to be the concentration of dinitrogen tetroxide over the concentration of nitrogen dioxide squared. But notice that this is just the inverse of the KEQ for the forward reaction. It's flipped. So if we want to solve for the KEQ will equal to the inverse of 0.212. That happens to give you 4.72. Let me show you another example. In this example, we have a forward reaction, and now we have that same forward reaction, but it's scaled up, so the coefficients have been doubled. This is what the equilibrium constant expression would be for this doubled reaction. And notice that that is the equivalent of taking this KEQ for the regular forward reaction and essentially squaring it. That would give us this value. So the KEQ value for doubling the coefficients is going to be the original KEQ value, but squared. So you can solve for that if you wish. In this next example, the forward reaction coefficients have been scaled down. So here's the original forward reaction. Notice that each one of the coefficients has been cut in half. I wrote the equilibrium constant expression for this scaled down reaction. And notice that to get that, I essentially had to take the original KEQ and take the square root of it. And doing so will give me this KEQ value. So to solve for that numerical value, I'll take the original KEQ value and simply take the square root of it. And that will give you your KEQ for the scaled down reaction. Here's a quick summary of lesson 2B, and that is we were looking at equilibrium constant expressions, which are expressions that relate the ratio of products to reactants for a reaction that has come to equilibrium. The value of that equilibrium constant will tell us whether our products predominate or our reactants predominate within our closed system. And since KEQ is so tied to stoichiometry, if we write a chemical reaction in a different way, scaling it up, scaling it down, writing it in reverse, that will affect the numerical value of the KEQ. And that's it.